All right, we're on. We ended this morning, Ben. Yeah. We ended this morning with I was telling you this difference between heat and temperature. Obviously, it takes heat to raise the temperature of something, but obviously, the more that something there is, the more heat it's going to take to raise the temperature by a given amount. And I told you about this unit that physicists defined, the calorie, as the unit of energy or heat that is required to raise the temperature of 1 gram of water by 1 degree. Okay, now the physicists quickly discovered that the amount of heat required to raise the temperature of something by a given amount didn't just depend on the weight or the volume of the material. And let me give you an example to make this clear. Let's say that we take let me switch to familiar temperatures. So we'll use the Fahrenheit scale here. So let's say we have a container that is filled with, say, alcohol. At room temperature, okay, so 70 degrees Fahrenheit. Now, let's say we have another container that has the same amount of water. And let's say we've heated this one up to, 180 degrees Fahrenheit. Now, we take a larger container, and we pour both of these in. Okay? Mix them together. So, water plus alcohol. And the question is, what temperature will it be at? Daniel? 125 degrees. Yeah, you'd think that. You add them? Oh, no, you know that wouldn't work, right? It has to be somewhere in the middle, because obviously if you take, if you could add them, you could take 2 containers of room temperature water, add them together, and they'd be twice as hot, right? So no, that's not going to work. But I mean, Daniel's guess was a good one, right? You'd think, well, we had the same amount of alcohol and water. You think when you add them together, temperature should just be down the middle. I mean, you know, for instance, if this were water instead of alcohol, and then if you just added the 2 waters together, you know the temperature would have to come out to 125 degrees, right? But it doesn't work if they're different different liquids. Turns out that if you actually do this experiment, well, let's just put down the guess of 125. And that is wrong. It turns out it comes out to about 140 degrees. Why? Good question. Well, what would you have to say in a case like this? Let me. Yeah, Troy.
That water, you need more heat to heat, you need more calories to heat up water than you do to heat up alcohol.
Yeah, that's exactly right. The water, it takes more calories, more energy to change the temperature of water than it does to change changing the temperature of alcohol. You can think of it this way: changing the temperature of alcohol is easier than changing the temperature of water. There's another way you can see this. Let's see. If you took these two original containers here, call this example 1. Okay, I'm done with that now. Let me go on to a slightly different example now. Let's take these same two containers and let's stick a thermometer in each of them. And let's start them out at room temperature, but put them both on the stove and start heating them up. Okay, now, or we're putting them both under the same fire, okay, so they're getting the same amount of heat. Now, what you'll see happening is that when this water, by the time the water has gone up, let's say by 40 degrees, okay, but at a certain point, the temperature of the water has been raised by 40 degrees. How much do you think the temperature of the alcohol has been raised? Troy?
Maybe 68 degrees or something.
70, turns out. It's about so putting them under the same heat, you just see the temperature of the alcohol going up faster than the temperature of the water. Now, notice this fits in perfectly with my previous example. If you look at what I did with the numbers in the previous example, I had the alcohol going up from 70 degrees up to 140 at the same time that the water dropped from 180 to 140. So the water dropped 40 degrees as the alcohol went up 70 degrees. Okay, so this forced scientists to realize that there's a property of materials, that different materials require different amounts of heat in order to raise their temperature, and that this is a property of a material, how much heat is required in order to raise its temperature. So it turns out that water is an unusual material. It takes a lot of heat to raise its temperature. Most materials require their temperature goes up quicker than the temperature of water does when you give them heat. Now, this was a well, physicists defined a property now called specific heat. And the specific heat of a material well, let's just use the words I've been using, of a substance is the amount of heat required to raise the temperature of 1 gram by 1 degree Celsius. Okay, so the and it's usually, it's measured in, so the units of this actually are calories per gram degree. Okay, so what that, what's the specific heat of water? Who knows? Troy?
Wasn't it 1 calorie?
Yeah, I mean, that was the definition of a calorie, right? So by definition, the specific heat of water is 1. Okay, and then all the other specific heats are measured relative to water. Okay, if you're working in calories. Now, what is the specific heat of alcohol going to be? Actually, you've got all the numbers that you need in order to figure it out. Daniel. 0.3. No, but I'm trying to figure out where you got that.
I lowered water to 0 degrees and alcohol down to 30 degrees.
Oh. Well, let me see. Would, well, is it going to be, I mean, you're right, it's going to be less than water, right? Because it requires less energy to go up a degree. Yeah, Nick. Yeah, you got it right. I mean, it's 4/7, right? Evan.
Wasn't this in Fahrenheit?
Oh, yeah, but it's going to be the same ratio. I mean, yeah, all that does is change the size of the unit, but right, it's going to be the same same ratio. Yeah. Notice here I didn't even specify whether I was talking Fahrenheit or Celsius because it didn't matter. Okay, so yeah, that's right. The specific heat of alcohol is going to be about 4/7, or around 0.6. If you work it out, it's more like 0.57, right? Now, well, let me give you some, let's see, some other specific heats. And you'll see that there's a lot of materials that it's even less. It takes doesn't take much heat at all to raise their temperatures. I mean, at least relative to the amount of heat it takes water. Troy.
Are there liquids that are more than 1? Is the specific heat is more than 1 or less than 1?
You know, what my chemistry book says is that water has one of the highest specific heats of any material, but it doesn't say it's the highest. So there must be materials that are even higher than 1, but I don't know what they are. Yeah.
Does this mean that if you put like a pot of alcohol and a pot of water in a stove, if you put your hand in the alcohol, it would feel hotter than the water?
Oh, would it feel hotter than the water? Is that right? Would it feel? Wait. Are they at the same temperature? You mean, or?
Yeah, after you put them on the
Well, I mean, if you put them both on the stove at the same time and started heating them up, the alcohol would heat up faster. So, I mean, if you put them on the stove, put them both on the stove for 2 minutes, and then stuck your hand, one hand in one and one hand in the other, yeah, the alcohol would definitely feel hotter. It would feel hotter because it is hotter. Now, now let me. Now you might wonder what all this has to do with the atomic theory. I'm getting there. There is going to be a connection. But at this point, the scientists themselves didn't see the connection, of course. They were just figuring out some interesting things about heat. So let me give you some specific heats that people measured. And I just want to look at a few metals here. So let's do aluminum.
How many are we going to look at?
Excuse me?
How many are we going to look at?
What?
How many metals are we going to
Oh, 4. I could have extended this list, but I think 4 is good enough to make the point I want to make. So let me do aluminum, copper, silver, and lead. And you can measure their specific heats. And remember, this is calories per gram degree. Now, how would you measure these specific heats? Let's say I gave you a chunk of lead and told you to tell me its specific heat. Nick? Oh. Yeah, you're on the. Yeah, you're on the right track. Do you have an idea, Evan?
Take well, if you had a measurement of them, you could take a gram each, and then.
Well, I mean, what if you? Here's what I would think of doing. Let's say you just heat the lead up. I mean, you have this chunk of lead. Okay, you heat it up, say, to 100 degrees Celsius. Okay, you've got a container of water that is at room temperature, say 20 degrees Celsius. Dump the lead in, and put the lead in the water. Then see what the final temperature is. Now, let's say that you had your you have 1 kilogram of lead, and you have 1 liter of water, which also weighs a kilogram. Okay, well, if the lead has the exact same heat capacity as the water, then when you take the 100-degree lead and you mix it with equal amount of 20-degree water, they would come to equilibrium at halfway in between, right, the 60 degrees. Okay, well, what you're going to find is, I already told you that the water has a much higher specific heat, and metals have low specific heat. So what's going to happen is the lead isn't going to be able to change the temperature of the water very much. And so the equilibrium temperature is going to be, actually in this case it turns out that it's like 23 degrees or something. I mean, it raises the temperature of the water a little bit, and the temperature of the lead comes, screaming down from from 100 to 23. But that ratio of the temperature change of the water to the temperature change of the lead gives you the specific heat of the lead. So that would be the way to work it out. Okay, now if you do that, here's what you find. Here's the kind of numbers you get. For aluminum, you get 0.22, okay, which means, if you mixed equal weights of aluminum and water that were at different temperatures, the aluminum would change its temperature by, say, 100 degrees in a case where the water only changed its temperature by 22 degrees. Okay, now for copper, it's even less. Yeah. Silver, even less. And lead is ridiculously low. Yeah. So that's why I said, in the case of the lead I told you about, that, it's barely able to change the temperature of the water at all. Okay, now. Troy.
Can you have a specific heat for hydrogen?
Oh, yeah. There is one. I just don't know what it is. But it would actually be, it would be high. I'm not,
Would it be higher than 1?
no, I don't believe it would be higher than 1. But it would be, it'd be close, though. Yeah. I'll look that up. The, now, before I gave you a list, well, let me lead into the next thing I want to tell you in this way. A couple of French physicists in 1819, they looked at these numbers and they had an interesting idea. I mean, nobody had made any headway at this point in understanding these numbers. It just seemed like there was this wide range of specific heats. I mean, wide range of, different materials required much different amounts of heat in order to raise their temperature by the same amount, and nobody knew why. And so these two French physicists had the idea, well, what if we don't think in terms of mass? What if we think in terms of atoms? What if we think in terms, what if we calculate a new quantity that no one's calculated before, which is the amount of heat required to raise the temperature of a certain number of atoms, okay, rather than the amount of heat required to raise the temperature of a certain weight. Okay, now, how would we calculate that? Nick? Well, no, you can't do that. They're too darn small. But we've already got all the information we need. Evan?
Well, if you know that if you could find the chemical composition
Yeah.
of lead, well, wait, is lead an element? No, it's
Yeah,
element.
lead's an
Well,
element.
if you know that a certain volume is going to have is going to have the same number of molecules in it.
Oh, okay, I see what you're saying. Yeah, for gases that would work.
Yeah.
See, for gases,
You have to have
gases, that's true. So you'd have to have it in gas state in order to work with volumes. But there's there's another way to do it. Because you don't want to, boil off all these metals. You have to get them pretty hot. before,
You can
Nick.
actually get like lead steam. Or you turn it into.
Well, I mean, you can get metal vapor. Yeah.
You have to get it hot enough to turn it into a liquid.
To
and then-
disassociate completely. Yeah, right. I mean, it's really, really hot. But the now, but how can you do this? Well, here's what Dulong and Pettit did. Imagine you define a new unit. See, they realized that the key to solving this problem, answering this question that they had, is in these atomic weights that I told you about this morning. So let's say we define a new unit. By the way, the names of these physicists are, I'll just give you the last names. Dulong and Petit. It's what?
It isn't with the little chart, right?
It isn't with.
The chart thing. It's not with.
No, I'm going to, first give you some background information, then erase it, and then complete this chart. So let me leave some room over here in your chart, okay? And make the notes I'm going to give you now, you can just make them below the chart. Okay. Here's what they had the idea of. Let's say we define something called a mole. Why they call it a mole, don't ask. But here's what a mole is. The number of atoms in 1 gram of hydrogen.
How many atoms is that?
They don't know. But yes.
Doesn't whenever you do something whole number come out to be like fractional number?
Yeah, I mean, if you really have to know, this number is 6 times 10 to the 23rd. It's a big number, yeah. There's a lot of atoms in a gram of hydrogen. But you don't need to know that right now. And Dulong and Pettit didn't know it. But yet they made this discovery I'm about to tell you about. But here's the key thing that they did know. If we define 1 mole as the number of atoms in a gram of hydrogen, well, let me ask you this question. How many atoms are there in 16 grams of oxygen? How many atoms are, this is an easy question. Yeah, number of atoms in 16 grams of oxygen. Come on, this is automatic, huh? Troy.
It's some amount of moles.
Yeah, it's some amount of moles, indeed. Exactly, 1 mole. Why? Explain it.
Because there's 1 gram of hydrogen weighs as much as 16 grams of oxygen.
Or, well, you didn't say that right, but I think you understand it, but you didn't say it right. an atom of oxygen is 16 times heavier than an atom of hydrogen, right? And that's what those atomic weights meant that we figured out before. I mean, we started out defining the weight of hydrogen as 1, right, basically. And then we worked out the relative weights of the other atoms. That's what those atomic weights are. So what came out of that was oxygen is 16 times, an oxygen atom is 16 times heavier than a hydrogen atom. Well, the same number of oxygen atoms has to weigh 16 grams then. Nick?
But then wouldn't that mean that wouldn't that mean that there's more than, it shouldn't be like 1 mole for 16 oxygen. Wouldn't it be more like 16 times 16? Because oxygen weighs more than hydrogen.
No, but an oxygen atom weighs 16 times as much as a hydrogen atom. So if you take the same number of oxygen atoms and hydrogen atoms, the group of oxygen atoms has to weigh 16 times more. Okay, so if you take a sample of oxygen that weighs 16 times more than your sample of hydrogen, then they have to have the same number of atoms, right?
Oh, yeah.
Yeah. Okay. So, did everybody get that? I don't see other heads nodding, but okay. Those atomic weights that I gave you this morning, they were the relative weights of the atoms. Okay. So, that means that, relative to hydrogen, which was called 1. So that means that if we define this mole unit as the number of atoms in 1 gram of hydrogen, then 1 mole is, all right, this one's pooped out. 1 mole of oxygen atoms weighs 16 grams. Right? Because each atom is 16 times heavier. So if you take the same number of atoms, the sample has to weigh 16 times as much.
Why just say weights? 16 grams.
Weight. Weight. And, let's just go one more. 1 mole of, I don't know, say, nitrogen. You want nitrogen? Okay. Exactly. Atoms weighs 14 grams. 1 mole of carbon atoms weighs 12 grams. 1 mole of lead atoms weighs 208. Okay, so for these metals that I have listed, let's write down first let's write down these atomic weights. Which we can now think of as grams per per mole. And that's what an atomic weight is, right? I mean, before,
What's the abbreviation of mole?
actually just write mole. Now, let's see if I can remember these numbers. Aluminum was 27, copper was 64, silver was, I believe, 108. And actually, lead I got wrong this morning. It's 207, not 208. I looked it up. I can't believe nobody caught that mistake.
Why?
Now,
Why is it?
just because I made a mistake and wrote 208 this morning when I should have written 207. Now, now remember what Dulong and Petit have in mind here. They want to now calculate the specific heat per number of atoms rather than per gram, per mole. So what do they have to do in order to switch these numbers from calories required per gram to calories required per mole? Do you see? Daniel.
You have to put the equations together, right? So calories times mole.
Yeah, I mean, what units do we get if I multiply this unit by grams per mole? What happens?
You get calories per mole.
You get calories per mole, right? Grams cancel out. Okay, so what does that mean that I should do here? Just multiply these numbers. Okay, so that gives me what is called molar specific heat, which is calories per mole degree. Okay, now, you multiply these things out, and I'm so brilliant I can do it in my head. Here's what you get. 5.9 for the first one. 5.9 for the second one. 6.1 for the third one. And suspense is building, and I can't find a pen to write with. 6.2 for, Yeah, copper is,
So you're multiplying or dividing the what?
I'm multiplying,
Those two.
yeah, the 0.22 times the 27, the 0.93 times the 64. And the amazing thing is, when you do that, I mean, except for minor deviations, you get the same number in all four cases. What does that mean? Troy?
That heat and atomic weight is connected somehow.
Well, definitely it means that. Yeah, I mean, what this is telling you is that no matter what the substance is, if you, or at least for these elements, I mean, they're all metals, but for these elements, no matter what the material is, if you take the same number of, if you have the same number of atoms in your sample, it takes the same amount of heat to raise their temperature. Whereas that wasn't true at all before when we were working in grams, right? So each atom, on the average, is absorbing the same amount of heat. More about that next time. But you can see that all of a sudden the atomic theory is making sense out of why these specific heats are the way they are. And it didn't make sense, these numbers didn't make sense to scientists at all. But coming up with one constant number is telling them something. And I'll elaborate on that next time.